I can say that I feel we're done with that. I'll put some practice with some of these on there, but I'm done with this one. They're not that interesting. This one was to show static. It was to show how to use a coordinate system and how to deal with the idea that forces can be in multiple directions. We're now going to do the elevator problem, and I want to do it kind of quickly, but not so quickly as to leave you guys, in the dust. The elevator problem is specific to demonstrate direction. So the elevator problem was specifically designed to see if you can deal with differences in acceleration, an understanding of when we deal with acceleration and when we don't, and did so in a straightforward manner. Let's start with the elevator problem. I need an elevator, so here's my elevator. And we're considering 3 different cases of the elevator. The first case is when the elevator is accelerating upwards. So the elevator starts at ground level, accelerates upwards at 2 meters per second squared. There's my person in the elevator. They hit the button, and the elevator obeys their command and accelerates upwards. The acceleration doesn't last long because elevators get up to speed pretty quick. So after a moment, the elevator is traveling at constant velocity of 1 meter per second. So here they are, they're in the elevator, trying not to fart, make sure the other people aren't uncomfortable. We reach the floor that we selected. The elevator has to stop, which means it has to slow down. It's moving upwards, so it must have an acceleration in the other direction to slow it down. Let's say it accelerates downwards, 3 meters per second squared, to come to rest. 3 situations of the elevator. Now, what I would like is for you to tell me the tension in the cable that acts on the elevator. That's what I want. Let's say the elevator has a combined mass with you of 500 kilograms. And I think you could probably agree with me that the mass of the elevator isn't going to change. So it's going to be 500 in all of these because nobody gets on or gets off before we get to the next floor. And I want to point out something important. The answer is not 1,000 or 1,500. A lot of people will tell me the answer is 1,000 because they'll multiply 2 times 500 and think that all of this was just for fun. No. So please, let's do the first one first together. And then I think I can leave you guys to do the other ones on your own after you see it done. So let's start with this situation and go through our set of steps. The one thing I will encourage here is that the elevator does not change. So in deciding whether this is a first or a second law problem, all you need to do is determine whether it's accelerating or not. And I clearly told you it was accelerating. So it's a second law problem. But you're going to draw 3 free body diagrams, 1 for each circumstance. And the one thing that is the same in all 3 of them is that the elevator's weight is 5,000 newtons each time. So whatever size arrow you draw for the first diagram should be the same size arrow for all 3 diagrams. It should be comparative. I should be able to compare the 3 diagrams together. Now, going through my list of forces, I will point out that the elevator is not touching a surface. Because it's not touching a surface, there's no normal force acting on the elevator. And with no normal force, there's no frictional force acting on the elevator. I'm going to look ahead to that. But there is a cable attached to the elevator. And because there's a cable attached to the elevator, there must be a tension acting on the elevator. And I don't think it's a particularly weird thing to say the tension is going to be upwards. But I'm not going to draw it in an arbitrary fashion. The tension must be greater than the weight. It must be. The only way the object accelerates is if the forces are unbalanced. And this is the only other force acting in the system. It must unbalance the weight of the elevator. Now I know I should move on to the next one, which is to apply a coordinate system. But this is a one-dimensional problem on purpose. I'm trying not to make it too tough yet. So here's my coordinate system. Upwards positive, downwards negative. So from here, net force equals ma. So net force in the y direction equals ma. It's only one dimension. Add up all the forces, take into account their direction, and set them equal to ma. That's what this set of instructions says. So add up all the forces, taking into consideration their direction. So tension minus 5,000 equals 500 times 2. And is there anybody concerned with where I got the 5,000 from? So weight is always going to be mg, where we will use 10 for g. So in this case, our weight is 500. That's the mass of the elevator, times g, which is 10. And that's where the 5,000 comes from. So, not a big stretch here, but the tension is going to be 6,000. Now, there's bigger implications here than this number. This number doesn't mean a whole lot to all of you. You don't know whether that's a big number or a small number. It's not the number. The important detail is that the cable you use to hold this elevator has to be able to withstand more than just the weight of the elevator. When the elevator is being pulled upwards, the cable has to not only support the elevator, but apply a bigger force to overcome the inertia of the elevator. This is about inertia. The elevator doesn't want to move. So if I want to make it move, I must pull on it with something harder than just the weight of the elevator. It's the only way to get it to move. And the more I pull on it, the more extra force I'm going to have to apply. If you buy a cable that can only support 5,000 newtons, because you say that's the maximum occupancy of the elevator, then you're going to have a problem. Because I am going to guarantee you the moment you start trying to move that elevator around, you're going to have to pull harder than the weight of the elevator. Of course, this is also why there is a maximum on elevators, to ensure that the system in place can actually withstand all of the forces it has to apply to get the elevator to move. Now, I think it's at this point where I can probably take a back seat and let you guys do the other two. All right? So let's do 5 minutes. So most all of you recognize that net force here is equal to 0. And in drawing them, I saw many of you did a great job of indicating that there's a downward force and drew an arrow that was the same size as the 5,000 newtons you drew before, which is what I'm trying to encourage. And then with that, drew an upward arrow that was more or less the same size as the downwards arrow, which is what I would expect to see, showing that the tension equals 5,000 newtons. Don't be distracted with a number here. Doesn't matter how fast the elevator is going. If it's traveling at a constant velocity, the net force is 0. Forces are balanced. It's over here where I started to see people capable of getting a numerical answer, but not necessarily capable of drawing a picture. And what I mean by that is you should clearly indicate to the person who's grading your paper that although this downward arrow is still 5,000 newtons, the only way the elevator can accelerate downwards is if the forces are unbalanced. There are a lot of people who want to switch and somehow make something else pull downwards on the elevator. That's not what happens. The cable attached to the elevator can only pull upwards because it's fastened to the top of the elevator. So what you must draw here must indicate that the upward force is clearly less than the downwards force. It is the weight of the elevator that stops the elevator. This also limits how fast the elevator can accelerate downwards. Meaning there's a threshold here. The elevator can't apply less than 0 newtons of force. That's a threshold. The tension can't push down on the elevator. It can only not pull up. So there's limits on what can be done. And that's going to be a consistent theme. It's not going to be this problem. There'll be a problem where I say, what is the limit to how fast the elevator can slow down? And you'll have to understand where the limits of the problem exist. The weight's not going to change. It's not like people are being ejected from the elevator. At the same time, net force equals MA here. And another problem some of you made is not recognizing that we still have to apply a coordinate system. That coordinate system not only applies to the force, but also applies to the acceleration. So when you've decided that up is positive, to be consistent, that will be tension minus 5,000 equals 500 times negative 3. Acceleration's downwards. If you've indicated downwards as negative, you have to apply that to every vector in your problem. But for the most part, most of you are acquiescing here. Keep this idea that these arrows, these downward arrows, should all have been around the same size. Comparative problems are becoming more frequent, and we need to be aware of these comparative problems. All right. Be aware, stupid little things happen when we mess with this problem. Like, what if I asked about the person and not the elevator? It's hilarious, but people will draw the person with a string coming off the top of their head. There's no tension acting on the person. How does the person inside the elevator accelerate? Yes, ma'am. The normal force. The only thing in contact with the person is the floor. So this person does not experience a tension. They experience a normal force and their weight. So it's going to be the normal force that determines how much they accelerate. In fact, it might not be well known to you guys, but your apparent weight, what you experience as gravity, is not you feeling gravity. You can't feel gravity. Gravity doesn't act on your center. It's not like we all have this dot inside of us, and that's where gravity acts. Gravity acts on every piece of your mass. And therefore, you can't actually feel gravity. What you feel is the effects of the normal force on your body. That's how you experience gravity. When the elevator accelerates upwards, you feel heavier because the normal force has to increase in order for you to accelerate upwards. And some of you are not really fully invested in this conversation, but if you're 60 kilograms, which is about 130 pounds, then your weight is 600 newtons on the ground. But in this elevator, your weight is 720 newtons. It's got to be. It's like 150 pounds. You feel heavier because the elevator is accelerating upwards. For the same reason that same 60 kilogram person, they only experience 420 newtons of weight when the elevator is slowing down. That's about 80 to 90 pounds. It's because they have reduced the normal force. For practice, you guys who are struggling should verify that it's 720 and 420. It'll make sure that you understand what's happening here. Or, if you really want to practice, have the elevator go down instead of up. See how that changes things. When do you feel more heavy, and when do you feel more light? we've got 15 minutes left or so. And, not quite 15 minutes. The next problem that we really have to take a look at is one that is probably the most common question in all of the AP exam. When it comes to Newton's law problems, they really lean into this one a lot. The inclined plane is the most likely Newton's law problem you'll be asked to solve. And they really like the inclined plane problem on the AP exam. There's a lot of reasons for it. The inclined plane can be used to demonstrate a lot of things. First, the inclined plane is a simple machine. There are 4 simple machines. Do you guys know all of the simple machines? Can anybody name one more simple machine? One more.
The Atwood machine?
The Atwood machine. It's not a simple machine. Yes, sir. The pulley is the simple machine. It can be used in an Atwood machine, but the pulley is another simple machine. There's 2 more left. Who knows what the other 2 are? Yes, sir. The wedge is the inclined plane. It's just used differently. So you can use the wedge to like split a log, and it would be similar to an inclined plane. Nope, you already tried. We've got to find somebody else. Lots of people went to school. Come on, middle school gave you all 4 of them. There's 2 more. Yes, sir? Pendulum is not a simple machine. Sorry. Yes, ma'am? The what? Spring is not a simple machine. Wow. Maybe we didn't learn this in middle school. Well, it's in the physical science curriculum for middle school, just so you know. I've had to read it. All right, I'm disappointed. I'll live with it. What we're looking at here is the inclined plane. And so inclined plane and wedge are both the same thing. They are one of the simple machines. The pulley is the one that usually most students pick up next. But almost always I get somebody who says lever, which is another simple machine. This is something that like the coyote would use to unlodge rocks to drop on a roadrunner. It's a lever. It's also like a teeter-totter or a seesaw is a lever. And the last one is one most people don't remember, but it's a wheel and axle. And these represent the 4 simple machines. Now, simple machines are not studies in force. Simple machines are studies in energy. Generally, the simple machine exchanges force for distance. That's generally what they do. They allow you to increase or decrease the amount of force you apply at the expense of distance. If you jack up your car, you're using a lever. The lever allows you to put in less force than the weight of the car. But you have to probably move your arm many, many meters compared to the few inches the car might be lifted. Now, if you're using a scissor jack, it's actually using an inclined plane because a screw is an inclined plane that's been wrapped around an axle. Now, most all of you had to use a simple machine to get to this classroom. Most of you can't jump to the 2nd floor. So you use a ramp, which allows you to apply less force over a longer distance. That's the stairs. They all exchange force for distance. The inclined plane is not a particularly interesting thing, but it does allow you to exchange force, apply less force to go up someplace. It does other things too. If you've ever put a screw into the wall, the screw might only be inserted this far, but you had to spin around and around and around to get it in. You exchanged the amount of force necessary to push the screw in with a distance you had to travel to get it into the wall. So all of these are considered simple machines. So let's say that I have a ramp that is inclined 25 degrees. And let's say that it is, for our starting place, frictionless. I'd like to know the acceleration of the box down the ramp. What I would really like is for you guys to create a clear and clean free body diagram of this arrangement. So for students who are doing this for the first time, be patient with yourself. You're only drawing 2 arrows. It's not so bad. We are limited on time, so I would like to make sure we complete this activity. So don't step around waiting for somebody else to get started. Go ahead and get started. Draw your dot and begin the process of drawing arrows. There's not many to draw. When we begin to draw these, you're ignoring the incline because there's nothing here about the incline at the beginning of this problem. Meaning the box has weight. Draw a downward arrow. Label it as such. It is setting the scale for the size of the rest of the arrows you will draw. And now I go down my list. I have 4 other things to test. Normal, tension, friction, air resistance. Is it in contact with the surface? It is. It's touching the incline. The incline can only apply a pushing normal force. Look at your notes. Normal forces are perpendicular to the surface in contact. I don't have a choice here. I have to do as instructed. The surface is one way. My arrow needs to be perpendicular to that surface. I don't get a choice. Are there any cables attached to the box? Is there any friction acting on the box? And we don't have air resistance unless we are told specifically to include it. This is it. These are the forces acting on the box. 2 arrows. Do they look balanced to you? They don't. Looks like there's more to one side than the other. So this has to be a situation in which the net force equals MA. Now, yes, technically that's a free body diagram, but you're not done. You have to apply a coordinate system in order to solve the problem. This one is the important one. So now that we've got our arrows drawn, and again, you've got a prescription here. You are asking 5 separate questions. Is there weight? Is there touching a surface? Is there a string attached? Is it sliding across a surface? Is there air resistance? You've got that list in front of you. Use it, please. But now you have to apply a coordinate system. 2 priorities. Align the x direction with the likely direction of acceleration. Is our box accelerating? Then you don't have a choice. That's the priority. You could choose a different one. It would be dumb. Follow the priority, which means line up the x direction with the ramp. That's the only direction the box can go. If you line up the x direction with the ramp, by definition, the normal force is lined up with the y direction. On an inclined plane, it is almost always going to be better for you to make the x direction down the ramp. Also, this part might be harder. There's an angle here. I don't have time before the bell rings to prove to you that it's at 25 degrees, but it is. I will prove it to you, but I don't have time today. I can tell you, though, that it's the weight that is off axis. So it is the weight that will have to be broken up into 2 components. The part of the weight that is into the plane, cosine, and the part of the weight that is down the plane, sine. The inclined plane is the most common problem in physics. So we will have to become accustomed to using it. And the test person's ability to make this a complicated question is a lot. For those of you who have been in physics, you understand. They are going to try and mess with this a lot. You need to be adept at setting this problem up. This is the part that accelerates the box down the ramp. For you guys who know that, just so we can skip to the end a bit, W sine theta equaled MA. So for those of you who went ahead and got the acceleration, this is mg sine theta, which equals MA. That was the answer. The acceleration of the box down the ramp. We didn't make it that far, but the bell rings like in a few seconds, so I will allow you guys to pack up. That it doesn't matter which set you use, but there are easier ways to do it than others. Most of you did exactly what I kind of expected you would do, which is you followed along with the way in which the problem was structured yesterday and applied the same things to this problem. Meaning, you started by indicating that the weight was down, which makes perfect sense. And the weight is 100 newtons. Here was where we got a little bit of some business that's not great. So 50 degrees, don't have a perfect angle for 50 degrees, but I know that both of these ropes are pulling upwards on the object, so I'm not convinced that either one of them will be 100 or more. I don't know that to be true, but I know that with the angle I chose here, some of this force is upwards. And I don't know that I need to make it much more than that, since there's going to be another force in this direction. And some of this force will be upwards. And together, the two of those things have to support the 100 newtons that's downwards. Now, you might not know to do what I did, but yeah, I drew the one that's to the left a little bit smaller, because I also know that this side has to be balanced by this side. So I'm trying to make sure that I'm being aware of this balance, and it might require that you draw it a couple different times. Now, here's where people did stuff that I was surprised. So let me, I don't know what I said. Is this one T2 and this one T1? First, I don't believe I have to say this in this room, but let me just make it kind of clear. The length of the ropes doesn't tell you the length of the length of the ropes does not tell you the force of tension. A longer rope is not more tension. I don't know that I need to say that, but some people think, well, this vector is this long because the rope is this long, and this vector is this long because the rope is that long. That's not true. Next, just a little different. So I'm trying to make it closer to what I know to be true. If you kept going with our list of steps, the next thing you're supposed to do is apply a coordinate system. And here's where people diverged. Many of you applied the coordinate system this way. I guess because this is the way we did it yesterday. That's all well and good. You can do any coordinate system you want. The coordinate system is there for you as a means of helping you organize the whole problem into one-dimensional problems. So if you did this, then you probably put the 50 degrees here. I know in the original problem, the 50 degrees was here. I wrote it down here in an attempt to help you with the directions of your forces. The 40 degrees is also listed here. That meant that this is 40 degrees. So then you break these up into components. So would we agree that this is what one of them will look like? Any problem with that? There is problems with that? Okay, so T2 cosine 50 and T2 sine 50. Any issue there? So similarly, components on this side with T1 cosine 40 and T1 sine 40. Is that good for you guys? All right, net force equals 0. So the amount of force on the left and right have to be summed to be 0. or they have to be equal to each other. So T2 cosine 50 minus T1 cosine 40 has to equal 0. And then I've got 2 forces upwards and 1 force downwards. So T1 sine 40 plus T2 sine 50 minus 100 has to equal 0. This is net force in the y direction. This is net force in the x direction, which both equal 0. Any questions about that? I just followed the set of steps that we talked about, broke my forces up into their component parts, and put the ones that were left and right in one equation and ones that were up and down in the other equation. Again, I'm saying these kinds of things out loud for the people who didn't know to do this, to give yourself more instruction about what it is you have to do. Once you put the coordinate system in place, you need to break up the forces into the x and y direction. Put all the x's together and all the y's together. Now, this is it. This is Newton's laws are done now. We have generated our relationship that matches this problem. Will it give you an answer? Will it tell you what T1 and T2 are? Yeah, but it's not going to be easy. I've got 2 equations with 2 unknowns, so I now have to do some substitution to get to my answer. It will work. You got lots of sines and cosines in there. You can hit your calculator and get all the numbers for sines and cosines and do your substitution, and you'll get your answer, and you'll get 64 and 77. But you missed a step. And I want to talk to the folks who missed the step, because a few of you didn't miss this step. We didn't have to do any of that. I put the 40 and the 50 here in the hopes that you would see that this is 90 degrees. That's why I put it there. Because I was hoping that if you saw that was 90 degrees, then perhaps a change of coordinate system would have served you a little bit more efficiently. Because if I make this my x direction and this my y direction, then this becomes 50 degrees. And now this will be my 2 components. I only have to break up one of the forces. So this will be 100 cosine 50, and this will be 100 sine 50. Yeah.
I put my angle on the 50 degrees on the other side. Can you show how why you put the angle there instead of on between the y and the force of gravity? So I put the 50 degrees.
I heard you. I'm trying to see if I can find an easy way to tell you. So don't ever confuse me not answering right away with not understanding the question. Sometimes it's just me trying to figure out the best way to answer your question, and also to provide you with an answer that's complete. And because if you have that question, I bet somebody else does. Let's look at this a little different. Would you agree with me that this is 50 degrees? Okay. So let me state that I'm going to change what I said a moment ago, and I'm going to do this a little different than I did it the last time. I'm going to take the x direction, and I'm going to rotate it to line up with T2. How many degrees would I have to rotate the x direction in order for it to line up with T2?
50 degrees.
50 degrees. So when I do that, and I rotate it to line up with the x direction, I've rotated it 50 degrees, right? Now, I can't rotate it 50 degrees without also rotating the y direction by the same amount. So now I have to take the y direction and rotate it this way 50 degrees. So that's what I'm going to have to do. That means that this has become the 50 degrees, not over there. Does that make sense? So I labeled them X and Y backwards, but that'll work now. Does that make sense to everybody why I did that and why the 50 degrees is there now? We're just turning the coordinates. Okay, so again, this is still going to be 100 cosine and 100 sine. And 100 sine. Do I have to explain that? We've been doing that for a while now. I'm hoping it's starting to sink in. Well, good. The x direction has T2 and 100 sine 50. That's the x direction. So net force in the x direction is 0. So T2 minus 100 sine 50 equals 0. The y direction has T1 and 100 cosine 50. So net force in the y direction equals 0. So T1 minus 100 cosine 50 equals 0. Would you agree this is easier? Yeah, sure is. You get the same answer. But, you know, that's easier by far. What's really interesting, though, is if you did it the other way, it will reduce down to this anyways. Because you're going to get these sines divided by cosines, multiplied by sines all over the place. It all reduces down to this anyways. So, they won't all be like this. This only worked because this was 90 degrees. If it was 70 degrees, well, then you would have no luck here. I'm telling you to be aware of this and to look out for it. It does make a difference. But the truth is, we could have chosen an axis that wasn't lined up with any of them if we want. I wouldn't. It would be hard. But you could. All right, so we've exhausted this one, haven't we? So today,